Electric circuits, section 1. Electric conduction, solid and liquid conductors. When electric power flows through a circuit, we find phenomena taking place outside of a conductor which direct the flow of power, and also inside thereof. The phenomena outside of a conductor are conditions of stress in space, which are called the electric field. The two main components of the electric field being the electromagnetic component, characterized by the circuit constant inductance, and the electrostatic component characterized by the electric circuit constant C. Inside of the conductor, we find a conversion of energy into heat. That is, electric power is consumed in the conductor, but what may be considered as a kind of resistance of the conductor to the flow of electric power, and so we speak of resistance of the conductor as an electric quantity representing the power consumption in the conductor. Electric conductors have been classified and divided into distinct groups. We must realize, however, that there are no distinct classes in nature, but a general transition from type to type. Metallic conductors. The first class of conductors are the metallic conductors. They can be characterized by a negative statement. That is, metallic conductors are those conductors in which the conduction of the electric current converts energy into no other form but heat. That is, a consumption of power takes place in a metallic conductor by a conversion into heat, and into heat only. Indirectly, we may get light if the heat produced raises the temperature high enough to get visible radiation, as in incandescent light filament, but this radiation is produced from heat, and directly the conversion of electric energy takes place into heat. Most of the metallic conductors cover, as regards the specific resistance, a rather narrow range between about 1.6 microohm per centimeter, with 1.6 times 10 to the minus 6 for copper, to about 100 microohm centimeter for cast iron, mercury, high resistance irons, etc. They therefore cover a range of less than 1 to 100. Resistance temperature characteristic, figure 1. Pure metals, number 1. Alloys. Resistance to temperature characteristic. A characteristic of metallic conductors is that the resistance is approximately constant, varying only slightly with the temperature, and this variation is a rise of resistance with increase of temperature. That is, they have a positive temperature coefficient. In the pure metals, the resistance apparently is approximately proportional to the absolute temperature. That is, the temperature coefficient of resistance is constant, and such that the resistance plotted as function of the temperature is a straight line which points towards the absolute zero temperature, or in other words, which prolonged backward towards falling temperature would reach zero at minus 273 centigrades. As illustrated by curves 1 on figure 1, thus resistance may be expressed by R equals R0 times T, where T is the absolute temperature. In alloys of metals, we generally find a much lower temperature coefficient and find that the resistance curve is no longer a straight line, but curved more or less, as illustrated by curve 2, figure 1. So that the range of zero temperature ranges of zero temperature coefficient as A in curve 2, and even ranges of negative temperature coefficient as at B in curve 2, figure 1, may be found in metallic conductors which are alloys, but the general trend is upward. That is, if we extend the investigation over a very wide range of temperature, we find that even in those alloys which have a negative temperature coefficient for a limited temperature range, The average temperature coefficient is positive for a very wide range of temperature. That is, the resistance is higher at very high and lower at very low temperatures, and the zero or negative coefficient occurs at the local flexure in the resistance curve. Number 3, the metallic conductors are the most important ones in industrial electrical engineering, so that when speaking of a conductor, practically always a metallic conductor is understood. The foremost reason is that the resistivity or specific resistance of all other classes of conductor is so very much higher that of metallic conductors, that for directing the flow of current, only metallic conductors can usually come into consideration. As even pure metals, the change of resistance of metallic conductors with change of temperature is small, about 1/3% per degree centigrade, and the temperature of most apparatus during their use does not vary over a wide range of temperature. The resistance of metallic conductors R is usually assumed as constant, and the value corresponding to the operating temperature chosen. However, for measuring temperature rise of electric currents, the increase of the conductor resistance is frequently employed, where the temperature range is very large, as between room temperature and operating temperature of an incandescent lamp filament, the change of resistance is very considerable. The resistance of the tungsten filament and its operating temperature is about 9 times its cold resistance in a vacuum lamp, 12 times in the gas-filled lamp. Thus, the metallic conductors are the most important. They require little discussion due to their constancy and absence of secondary energy transformation. Iron makes an exception among the pure metals in that it has an abnormally high temperature coefficient, about 30% higher than other pure metals, and at red heat, when approaching the temperature where the iron ceases to be magnetizable, the temperature coefficient becomes still higher under the temperature is reached where the iron until the temperature is reached where the iron ceases to be magnetic. At this point, its temperature coefficient becomes that of the other pure metals. Iron wire, usually mounted in hydrogen to keep it from oxidizing, thus finds a use as serious resistance for current limitations in vacuum arc circuits. Electrolytic conductors. The conductors of the second class are the electrolytic conductors. The characteristic is that conduction is accomplished by chemical action. The specific resistance of the electrolytic conductors is, in general, is about 1,000,000 times higher than that of the metallic conductors. They're either fused compounds or solutions of compounds in solvents, ranging in resistivity from 1.3 ohm centimeter in 30% nitric acid as acids and nitric acid, and still lower in fused salts to about 10,000 ohm centimeter in pure river water, and from there up to infinity distilled water, alcohol, oils. They're all liquids, and when frozen become insulators. Characteristic of electrolytic conductors is the negative temperature coefficient of resistance. The resistance decreases with increasing temperature, not in a straight line, but in a curved line, as illustrated by curve 3 in figure 1. Figure 3. Curve 3 in figure 1. When dealing with electrolytical resistances, in many cases it is more convenient and gives a better insight into the character of the conductor by not considering the resistance as a function of the temperature, but the voltage consumed by the conductor as a function of the current under stationary condition. In this case, With increasing current and so increasing power consumption, the temperature also rises, and the curve of voltage for increasing current so illustrates the electrical effect of increasing temperature. The advantage of this method is that in many cases we get a better view of the action of the conductor in an electric circuit by eliminating the temperature and relating only electrical quantities with each other, such volt-ampere characteristic of electric conductors can easily and very accurately be determined, and if desired by the radiation law approximate values of the temperature be derived, and therefore the temperature resistance curve calculated with a direct measurement of the resistance over a very wide range of temperature is extremely difficult and often no more accurate. Right. So volts vertical and amperes horizontal. In figure 2, therefore, are shown such volt-ampere characteristics of conductors. The dotted straight line is the curve of absolutely constant resistance, which does not exist. Curve 1 and 2 show characteristic of metallic conductors. Curve 3 of electrolytic conductors, as seen for higher currents. 1 and 2 rise faster, and number 3 slower than for low currents. It must be realized, however, that the volt-ampere characteristic depends not only on the material of the conductor as the temperature resistivity curve, but also on the size and shape of the conductor and its surroundings. For a long and thin conductor in horizontal position in air, it would be materially different numerically from that of a short and thick conductor in different position at different surrounding temperature. However, qualitatively, it would have the same characteristics, the same characteristic deviation from straight line, etc., merely shifted in the numerical values. Thus, it characterizes the general nature of the conductor, but where comparisons between different conductor materials are required, either they have to be used in the same shape and position when determining their volt-ampere characteristics, or the volt-ampere characteristics have to be reduced to the resistivity temperature characteristics. The volt-ampere characteristics become of special importance with those conductors to which the term resistivity is not physically applicable, and therefore the effective resistivities of little meaning, as in gas and vapor conductors, arcs, etc. The electrolytic conductor is characterized by chemical action accompanying the conductor. This chemical action follows Faraday's law. The amount of chemical action is proportional to the current and the chemical equivalent of the reaction. The product of the reaction appears as at the terminus of electrodes between the electrolytic conductor or electrolyte and the metallic conductors. Approximately 0.01 milligram of hydrogen are produced per coulomb of ampere second. From this electrochemical equivalent of hydrogen, all other chemical reactions can easily be calculated from atomic weight and valency. For instance, copper with atomic weight 63 and valency 2 has the equivalent 63 divided by 2 equals 31.5, and copper therefore is deposited at the negative terminal of cathode, or dissolved at the positive terminal or anode at the rate of 0.315 milligram per ampere second. Aluminium atomic weight 28 and valency 3 at the rate of 0.093 milligram per ampere second, etc. The chemical reaction of the electrodes represents an energy transformation between electrical and chemical energy, and as the rate of electrical energy supply is given by current times voltage. It follows that a voltage drop of potential difference occur at the electrodes in the electrolyte. This is in opposition to the current, or a counter EMF, the counter EMF of electrochemical polarization, and thus consumes energy. If the chemical reaction requires energy, as deposition of copper from a solution of copper salt, it is in the same direction as the current, thus producing electric energy. If the chemical reaction produces energy, as the dissolution of copper from the anode. As the chemical reaction, and therefore the energy required for it, is proportional to the current, the potential drop at the electrode is independent of the current density, or constant for the same chemical reaction and temperature, except insofar as secondary reactions interfere. It can be calculated from the chemical energy of the reaction and the amount of a chemical reaction as given by Faraday's law. For instance, 1 amp sec deposits 0.315 milligram of copper. The voltage drop E, or polarization voltage, thus must be such that E volts times 1 amp and 1 amp sec, or E watt times E watt second, or joules, equals the chemical reaction energy of 0.315 milligram copper in combining to the compound from which it is deposited in the electrolyte. If the two electrodes are the same and in the same electrolyte at the same temperature and no secondary reaction occurs, the reactions are the same but in opposite direction at the two electrodes, as the deposition of copper from a copper sulfate solution at the cathode, solution of copper at the copper sulfate solution at the cathode, solution of copper at the anode. Once again, if the two electrodes are the same and in the same electrolyte at the same temperature, and so no secondary reaction occurs, the reactions are the same but in opposite direction at the two electrodes, as the position of copper from a copper sulfate solution at the cathode, solution of copper at the anode. In this case, the two potential differences are equal and opposite. The resultant thus zero, and it is said that no polarization occurs. If the two reactions at the anode and the cathode are different, as the dissolution of zinc at the anode, the deposition of copper at the cathode, or the production of oxygen at the carbon anode, and the deposition of zinc at the cathode, then the two potential differences are unequal and the resultant remains. This may be in the same direction as the current, producing electric energy, or in an opposite direction, consuming electric energy. In the first case, copper deposition and zinc dissolution, the chemical energy set free by the dissolution of the zinc and the voltage produced by it is greater than the chemical energy consumed in the deposition of copper and the voltage consumed by it, and the resultant of the two potential differences at the electrode thus is in the same direction as the current, hence may produce this current. Such a device then transforms chemical energy into electrical energy and is called a primary cell, and a number of them a battery. In the second case, zinc deposition and oxygen production at the anode, the resultant of the two potential differences at the electrodes is in opposition to the current. That is, the device consumes electric energy and converts it into chemical energy as electrolytic cell. Both arrangements are extensively used. The battery for producing electric power, especially in small amounts, as for hand lamps and the operation of house bells, etc. The electrolytic cell is used extensively in the industries for the production of metals and aluminum, magnesium, calcium, etc., for refining of metals as copper, etc., and constitutes one of the most important industrial applications of electric power. A device which can efficiently be used alternately as battery and the electrolytic cell is the secondary cell, or storage battery. Thus, in the lead storage battery, when discharging, the chemical reaction at the anode is conversion of lead peroxide into lead oxide. Of the cathode, the conversion of lead into lead oxide in charging, the reverse reaction occurs. Specifically, as polarization cell is understood a combination of an electrolytic conductor with the two electrodes of such character that no permanent change occurs during the passage of the current. Such, for instance, consists of two platinum electrodes in diluted sulfuric acid. During the passage of the current, hydrogen is given off at the cathode and an oxygen at the anode, but the terminals and electrolyte remains the same, assuming that the small amount dissociated water is replaced. In such a polarization cell, if E equals counter EMF of polarization, corresponding to the chemical energy of dissociation of water and approximately 1.6 volts at constant temperature and thus constant resistance of the electrolyte, the current I is proportional to the voltage E minus the counter EMF of polarization. I equals E minus E0 divided by R. In such a case, the curve 3 of figure 2 would, with decreasing current, not go down to 0 volts, but will reach 0 amperes at a voltage E equals E0, and its lower part would have the shape as shown in figure 3. Let's check. That is, the current begins at voltage E0, and below this voltage only a very small diffusion current flows. When dealing with electrolytic conductors, as when measuring their resistance, the counter EMF of polarization thus must be considered, and with impressed voltages less than the polarization voltage, no permanent current flows through the electrolyte, or rather only a very small leakage current or diffusion current, as shown in figure 3. When closing the circuit, however, a transient current flows. In the moment of circuit closing, no counter EMF exists, and current flows under the full impressed voltage. This current, however, electrolytically produces a hydrogen and an oxygen film at the electrodes, and with their gradual formation, the counter EMF of polarization increases and decreases the current until it finally stops it. The duration of this transient depends on the resistance of the electrolyte and on the surface of the electrodes, but usually is fairly short. This transient becomes a permanent with alternating impressed voltage. That's when an alternating voltage of maximum value lower than the polarization voltage is impressed upon an electrolytic cell, an alternating current flows through the cell, which produces the hydrogen and oxygen films, which hold back the current flow by the current counter EMF. The current thus flows ahead of the voltage or counter EMF, which it produces as a leading current, and the polarization cell thus acts like a condenser and is called an electrolytic condenser. It has an enormous electrostatic capacity or effective capacity, but can stand low voltage only 1 volt or less, and therefore is of limited industrial value. Chemical action requires appreciable time, such as electrolytic condensers show at commercial frequencies high losses of power by what may be called chemical hysteresis, and therefore low efficiency, but they are alleged to become efficient at very low frequencies. For reasons they have been for this reason, they have been proposed in the secondaries of induction motors for power factor compensation. Iron plates in alkaline solution as sodium carbonate are often considered for this purpose. Note the aluminum cell consisting of two aluminum plates with an electrolyte which does not attack aluminum often is called the electrolytic condenser, as its current is leading, that is, it acts as a capacity. It is, however, not an electrolytic condenser, and the counter EMF, which gives the capacity effect, is not electrolytic polarization. The aluminum cell is a true electrostatic condenser in which the film of alumina formed on the positive aluminum plates is the dielectric. Its characteristic is that the condenser is self-healing. That is, a puncture of the aluminum film causes a current to flow, which electrolytically produces alumina at the puncture hole and so closes it. The capacity is very high due to the great thinness of the film. but the energy losses are considerable due to the continual puncture and repair of the dielectric film. Pyrolytic conductor. Pyroelectric. The third class of conductors are the pyroelectric conductors of pyroelectrolytes. In some features, they are intermediate between the metallic conductors and the electrolytes, but in their essential characteristics, they are outside of the range of either. The metallic conductors, as well as the electrolytic conductors, give a volt-ampere characteristic in which, with increase of current, the voltage rises faster than the current in the metallic conductors. Due to their positive temperature coefficient, slower than the current in the electrolytes due to their negative temperature coefficient. The characteristic of the pyroelectric conductors, however, is such a very high negative temperature coefficient of resistance, that is, such rapid decrease of resistance with increase of temperature, that over a wide range of current, the voltage decreases with increase of current. Their volt-ampere characteristic thus has a shape as shown diagrammatically in figure 4. Though not all such conductors may show the complete curve, or parts of the curve may be physically unattainable for a small current range. Number 1. The voltage increase is approximately proportional to the current and sometimes slightly faster, showing the positive temperature coefficient of metallic conduction. At A, the temperature coefficient changes from positive to negative and the voltage begins to increase slower than the current, similar to the in electrolyte range. The negative temperature coefficient rapidly increases and the voltage rise becomes slower until a point B. The negative temperature coefficient has become so large that the voltage begins to decrease again with increasing current, range 3. The maximum voltage point B thus divides the range of rising characteristic 1 and 2 from that of decreasing characteristic 3. The negative temperature coefficient reaches a maximum and then decreases again until a point C. The negative temperature coefficient has fallen so that beyond the minimum voltage point C, the voltage again increases with increasing current, range 4. Though the temperature coefficient remains negative like in electrolytic conductors. In range 1, the conduction is purely metallic. In range 4, it becomes purely electrolytic and is usually accompanied by chemical action. Range 1 and point 8 often are absent, and the conduction begins already with a slight negative temperature coefficient. The complete curve, figure 4, can be observed only in few substances such as magnetite. Minimum voltage point C and range often is unattainable by the conductor material melting or being otherwise destroyed by heat before it is reached. For example, in the case with cast silicon, the maximum voltage point B often is unattainable and the passage from range 2 to 3 by increasing the current therefore not feasible, because the maximum voltage point B is so high that disruptive discharge occurs before it is reached. Such, for instance, is the case in glass, the Nernst lamp conductor, etc. The curve figure 3 is drawn only diagrammatically and the lower current range exaggerated to show the characteristics. Usually the current at point B is very small compared with that at point C, rarely more than 100 of it, and the actual proportion more nearly represented by figure 5. With pyroelectric conductors of very high value of the voltage B, the current is in range 1 and 2 may not exceed 1 millionth of that at 3. Therefore, such voltage ampere characteristics I can't often plotted with square root of I as a abscissa to show the range in better proportions. Pyrolytic conductors are metallic silicon, boron, some forms of carbon, anthracite, many metallic oxides, especially those of the formula M squared, M2, M2, 3, or O4, where M2 is a bivalent, M3 a trivalent metal, magnetite, chromite, metallic sulfides, silicates such as glass, many salts, etc. Intimate mixture of conductors as graphite, coke, powdered metal with no conductors as clay, carborundum, cement also have pyrolytic conduction. Such are used, for instance, as resistance rods in lightning arresters in some rheostats, as cement resistances for high frequency power dissipation in reactances. Many, if not all, so-called insulators probably are in reality pyroelectric conductors in which the maximum voltage point B is so high that the range free of decreasing characteristics can be reached only by application of external heat, as in the enhanced lamp conductor, who cannot be reached at all because chemical dissociation begins below its temperature as in organic insulators. Once again, look at the graph 1, 2, 3, 4, 1, A, B, C. Figure 6 shows the volt-ampere characteristic of two rods of cast silicon, 10 inches long and 0.22 inches in diameter, with square root I as abscisca, as horizontal. Volt amperes, volts, or the square root of amperes as horizontal, and volts as vertical. And figure 7, their approximate temperature resistance. Okay, cannot be all shown, but let's read the description. Figure 7, their approximate temperature resistance characteristics. The curve 2 of figure 7 is replotted in figure 8. Curve 2. Resistance temperature characteristic of cast silicon. Resistivity in ohm centimeter. So we have temperature on the left. We have no, we don't have temperature on the left. What is it? Okay, this is to be determined. The approximate temperature resistant characteristics. The curve 2 of figures is replotted in figure 8 with log R as ordinates. Where the resistivity varies over a very wide range, it often is preferable to plot the logarithm of the resistivity. It is interesting to note that the range 3 of curve 2 between 700 and 1400 degrees Celsius is within the errors of the observation represented by the expression R equals 0.01 e to the minus 9080 over T, where T is the absolute temperature minus 273 centimeters as 0 point. The difference between the two silicon rods is that the one contains 1.4%, the other only 0.1% carbon. Besides this, the impurities are less than 1%. As in these silicon rods, the range 4 is not yet reached at the melting point. Figure 9 shows volt ampere characteristics with square root of I as abscisca. In figure 10, the approximate resistance temperature characteristic derived therefrom with log R as ordinates, or of a magnetic rod 6-inch long and 3/4 inch in diameter, consisting of 90% magnetite. Fe3 0.04 magnetite is Fe3O4, 9% chromite FeCr2O4, and 1% sodium silicate sintered together. As a result of these volt ampere characteristics, figure 4 to 10 paralytic conductors structural elements of an electric circuit show some very interesting effects, which may be illustrated on a magnetic rod, figure 9. The maximum terminal voltage which can exist across this rod is in stationary condition is 25 volts at 1 amp. With increasing with increasing terminal voltage, the current thus gradually increases until 25 volts is reached, and then without further increase of the impressed voltage, the current rapidly rises to short circuit values. Thus, such resistances can be used as excess voltage cutout, or when connected between circuits and ground as excess voltage grounding device below 24 volts. It bypasses a negligible current only, but if the voltage rises above 24 volts, it short circuits the voltage and so stops the further rise of operates the circuit breaker, etc. As the decrease of resistance is the result of temperature rise, it's not instantaneous, thus the rod does not react on transient voltage rises, but only on lasting ones. Within a considerable voltage range between 16 and 24 volts, three values of current exist for the same terminal voltage. Thus, at 20 volts between the terminals of the rod in figure 9, the current may be 0.02 amp or 4.1 amp or 36 amp. That is in series in a constant current circuit of 4.1 amp. The rod would show the same terminal voltage as in a 0.02 amp or a 3.36 amp constant current circuit, 20 volts. On constant potential supply, however, only the range 1 to 2 and the range 4 is stable, but the range 3 is unstable. And here we have a conductor which is unstable in a certain range of currents from point B at 1 amp to point C at 20 amps. At 20 volts impressed upon the rod, 0.02 amp may pass through it, and the conditions are stable. That is, a tendency to increase of current would check itself by requiring an increase of voltage beyond that supplied, and decrease of current would reduce the voltage consumption below that employed, and thus be checked. The same impressed 20 volts, 36 amps may pass through the rod, or 1,800 times as much as before, and the condition again are stable. A current of 4.1 amp also would consume a terminal voltage of 20, but the condition now is unstable. If the current increases ever so little by a momentary voltage rise, then the voltage consumed by the rod decreases because it becomes less than the terminal voltage of 20, and the current thus increases by a supply voltage exceeding the consumed voltage. This, however, still further decreases the consumed voltage and thereby increases the current, and the current rapidly rises until conditions become stable at 36 amp. Inversely, a momentary decrease of the current below 4.1 amp increases the voltage required by the rod, and this higher voltage not being not being available at constant supply voltage, the current decreases. Resistivity temperature characteristic of magnetite rod in degrees. This, however, still further increases the required voltage and decreases the current until conditions become stable at 0.2 amp. With the silicon rod 2 of figure 6 on constant potential supply with increasing voltage, the current and the temperature increases gradually until 57.5 volts are reached at about 450 centigrades. Then, without further voltage increase, current and the temperature rapidly and increase until the rod melts. Thus, condition of stability of a conductor on constant voltage supply is that the volt ampere characteristic is rising. That is, an increase of current requires an increase of terminal voltage. A conductor with falling volt ampere characteristic, that is a conductor which with increase of current the terminal voltage decreases, is unstable on constant potential supply. An important application of pyrolytic conduction has been the glower of the Nernst lamp, which before the development of the tungsten lamp was extensively used for illumination. Pyroelectrolytes cover the widest range of conductivities. The alloys of silicon with iron and other metals give, depending on their composition, resistivities from those of the pure metals up to the lower resistivities of electrolyte 1 ohm per centimeter cubed. Borides, carbides, nitrates, oxides, etc. gave values from 1 ohm per square per centimeter cube or less up to megaohms per centimeter cubed and gradually merge into the materials which usually are classed as insulators. Pyroelectric conductors thus are almost the only ones available in the resistivity range between the metals 0.0001 ohms centimeter and the electrolytes 1 ohm centimeter. Pyroelectrolytic conductors are industrially used to a considerable extent, since they are the only solid conductors which have resistivities much higher than metallic conductors. In most of the industrial uses, however, the dropping volt ampere characteristic is not of an advantage. It's often objectionable, and the use is limited to the range 1 and 2 of figure 3. If therefore if it therefore is of importance to realize their pyrolytic characteristics and the effect which they have when overlooked beyond the maximum voltage point. Thus, so-called graphite resistances or carborundum resistances used in series to lightning arresters to limit the discharge when exposed to continual discharge for a sufficient time to reach high temperature may practically short circuit and thereby fail to limit the current.